and Ricard Alert, and I'm in the Max-Planck-Institut for the Physics of Complex Systems in Dresden, and I'll tell you about part of my work today, but in general, it's about active matter and applying it to understand collective cell behavior.
And I think I don't need any extra introduction, so please go ahead, yes.
Thanks. Okay, so as everyone, I wanted to start by thanking the organizers. Thank you for putting this together. It's been super nice so far, and not only, yeah, everyone, yes, and not only thanking you, but actually congratulating you, because I thought, you know, last week's workshop was super good. So thanks for that. So today I wanted to talk about how cells find their weights. And so in particular, I want to talk about two mechanisms of guidance of cell migration, which are Durotaxis and frictiotaxis. And so what this means is Durotaxis means directed cell migration along gradients of substrate stiffness, and frictiotaxis means migration along gradient of substrate friction. Okay, and you'll see that these two are connected. And I want to apologize to Silke because she's already heard this story, so you know, second time for you, sorry. So let's see. Yeah, so the first part of the story is about this work that actually tries to you know, generalize the idea of wetting to active fluids, and then use this to understand collective durotaxis. So durotaxis in groups of clusters of cells, and in particular how to make collective durotaxis optimal, meaning that there's a particular substrate stiffness at which durotaxis is fastest. Okay, so this is this notion of optimal collective durotaxis through the physics of active wetting. And so this was a collaboration between theory and experiments. The experiments were done by Macià Pellarès in the lab of Xavier Trepat in Barcelona, and co-advised by Raymond Sunyer. And the theory was done by Irina Pujolma in the lab of Jaume Casademont, and co-advised by Raymond. And so let me start by reviewing a bit the history of durotaxis. And so the first ever observation was in single cells in the lab of Yuli Wang in year 2000. And what they saw is a cell that was moving on a substrate with a stiffness gradient and was moving from the left to the right, so from soft to stiffer areas of the substrate. So this was, you know, the first observation of durotaxis, very exciting. But then the excitement faded a bit because you know, they realized that this type of directed cell migration was less efficient than well-known types of directed cell migration, for example, guided by chemical gradients. So durotaxis was relatively inefficient compared to chemotaxis. But then the excitement came back in the year 2016, when in the lab of Xavier Trepat, they actually discovered that durotaxis can also take place collectively in cell collective. And so in particular, they looked at cell monolayers spreading on substrate with a stiffness gradient, and they found that this spreading is asymmetric, as you can see. The monolayer spreads more on the stiff side than on the soft side. And so this was exciting because now these collective systems can sense much shallower gradients in stiffness, and therefore durotaxis is much more efficient at the collective level than at the single cell level. But then the other thing that is important and I want to point out is that this is actually an asymmetric expansion. It's not really a coherent translation of the entire tissue toward higher stiffnesses. And this is something I'll come back to in a second. So how do you measure? Yeah, so this is not a claim that I'm making there are no measurements of that, let's say, but what's true is that in this case, for a given gradient in substrate stiffness, single cell cannot perform durotaxis, but the collective can. And the hypothesis of how this happens is because they actually span a much broader range of the gradient, and therefore can sense the difference where a single cell should. But there are no good measurements of efficiencies, at least that I know of. So then the next bit of history that I want to review is very recent. A couple of years ago, Adam Schellert and Roberto Mayor discovered durotaxis in vivo, and they did it by looking at the cell population known as the neural crest cells. That is a population of cells that, you know, in their example, in the frog embryo, moves from the back of the embryo to the front of the embryo to give rise to many structures that will develop into the skull and the face of the animal. And this directed motion happens guided by a gradient in the stiffness of the underlying tissue. Okay, so this is Durotaxis in vivo. You can see these cells moving from the back to the front, avoiding the eyeball. And then what's interesting is that they can take these cells and put them ex vivo on synthetic substrates. And when the substrate has a uniform stiffness, the cluster doesn't move. But when the substrate has a stiffness gradient, then the cluster performs Durotaxis. Okay. And so here I want to point out two things again. One is that this time, this is not asymmetric spreading anymore. This is now a coherent translation of the entire cluster towards high stability. And that these are no longer monolayers of cells, but they are three-dimensional cell clusters. And so if we want to understand this process, and in particular the coherent translation aspect, we have to understand the three-dimensional shape of these clusters. And so we can think about how these clusters actually wet the substrate at a particular stiffness. And so this was the first thing that we then did in the experiments in the lab of Xavier Drapat. And so they just took clusters of cells and put them on substrates of uniform stiffness, but different stiffness. Okay. And what you can see is that on soft substrates, the clusters remain rather spherical, and we would say they do not wet the substrate. And then at higher stiffnesses, the clusters spread very well as monolayers, and they fully wet the substrate. And so you can take still images of actin, and you can see again, that these are rather non-wetting, and these are very strongly wetting at higher stiffnesses. And so if you measure then contact angles, you can also see that the contact angle decreases with stiffness, again showing this increased tendency of wetting at higher stiffness. Okay. I would associate it to a different amount of traction force that cells exert on different stiffnesses. But whether that has implications for the phenotype of these cells, I don't know.
Okay, I guess maybe you're going to say this. I mean, is it always that you move faster or steeper, or does it matter in the kind of conditions?
This depends on conditions, but you'll see that the way we understand it and we model it is based on the fact that the traction forces are bigger for these guys. And so they also have the potential of moving faster. But then friction might also be higher, and so these two effects will be.
But the roughness is the same.
Yes, it's something that's very hard to control for, but in principle, it's the same. Yes, it could affect the wetting. But you'll see, we can come back at this at the end, because I'll talk about something that could look like thinning, and maybe at that point we can wonder about roughness again.
So in what sense, like at the 200 MBA, what sense is it still a cluster? Like following up on Toka's question, it does move quite mesenchymal. You check for mesenchymal markers?
No, okay. We didn't. And so these are all epithelial cells in principle. Now, whether they change their phenotype when you change the substrate stiffness, that could happen. But yeah,
are they
so
less stable as a cluster?
They are stable as a cluster.
Are they less stable as a cluster?
What do you mean less stable?
They sort of they shift, melt apart.
So they certainly change shape much more here than there. Here they remain rather spherical and not much happens. Here they do, the contour changes its shape. They can also fuse with other clusters if they get into contact. And then other than that, they perform some diffusive motion on the substrate.
You observe that if some of these, you put them in softer substrate, that will work.
Yes. So this, we haven't done that, but I'm guessing they will revert, because what we did in previous experiments that I'll discuss later is to actually, we showed that this wetting transition is reversible by playing with myosin contractility. So if you use blebistatin, for example, then you can get rid of the traction forces that promote spreading, and the tissue will retract again. And you can, what we did was, for example, so we had an experimental protocol that was inducing de-wetting. And so to show that the transition was reversible, we just let the system run, and then once it starts de-wetting, then you can actually interfere with contractility, and then it will re-wet. So in that sense, I'm guessing that if you now translate one of these clusters into a different substrate, they will also adapt. Great. Okay, so then the one thing that I want to show you about this type of experiments is that I think one of the nice things is that in the experiments they can measure traction forces. And there are two pieces of evidence from the traction forces that I think are important to point out. Here, what I'm comparing is the tractions generated by two clusters at different substrate stiffnesses, two standard substrate stiffnesses. And the two things that I want to point out is that the tractions are stronger on the stiffer substrate. You can see the arrows are bigger here than there. And then if we focus on the three-dimensional, the out-of-plane component of the tractions, then what we see is that on, you can see it here as well on any of the projections that you look at, you always see upward forces at the edge of the cluster, and then downward forces in the center of the cluster. And this is consistent with these clusters having some surface tension that pulls on the substrate at the edge, and then building up a Laplace pressure that pushes on the substrate in the center. Okay, so these are two ingredients of evidence that we see in the data that will be in the model that we're going to build for this. Okay, and then you can ask the final question, which is, now let's put this on a gradient of stiffness, and let's see if they do Durotaxis, and they do. I think it's easier to see here in the center, but if you look everywhere, they perform Durotaxis from soft. They move from soft to stiff areas, and then the next thing was to quantify this Durotactic motion. And here's the first surprise. So when we quantify the velocity of Durotaxis, what we see is that it's non-monotonic with the stiffness of the substrate. So this is the local stiffness, and what you can see is that the velocity of clusters first increases with stiffness, and then it decreases again. Okay, and so this was the first surprise for us. And so we then built a model that tries to explain this observation. And so the idea for the model is to build a model of three-dimensional active questions.
Scaling this cluster size and compare. That's probably the two here, but if you get into more agenda.
Yeah, so we just had two categories here. We tried with many more, but then the data, is noisy enough and becomes even noisier. So it's hard to say. But yes, this is something that is also worth pointing, which is that the velocity increases with the size of the clusters, at least with these two categories. And this is something that we also studied previously, so we were not surprised by that. And this is something that the model also recapitulates.
For what I think we were what we did first, we were not told they have a direct relation. They move the bottom of the runner of the recent time. You see something in the concept of of the diffusion regime. And not really changing a lot. So it would be interesting. It would be interesting to change the amount of time that you are using to estimate your velocity.
Yes. So this is also something that we played with, and so to estimate these velocities, we used a time difference that was longer than the persistence time, so that in principle we would only pick the directed part of the motion, but it's not easy to do that actually. So yeah, that's a good point. Okay, so then the model, the way we thought about it is these clusters are like three-dimensional active droplets, and so we wanted to build the minimal model of three-dimensional active web. And so
does it need to be three-dimensional?
Yes, you'll see that's it needs to have an out of plane forces as well. That's what we had before, so this is what I want to move on to now. What we had before is a model for two-dimensional active webbing. This is not enough to capture the
In some of the two dimensions, there's a height and then the actual rate.
No, when I say 2D, I mean on the plane. Yeah. So it had no height, or it had a uniform height. And now if we want to understand the observation that I presented, we need really a profile in the
You need to be in that direction.
No, we don't need to be in that direction. No, it would be
You need to be modeled with
Exactly.
that.
yes. Yeah, but
So backlog, okay, so you know the stiffness of each cell,
the stiffness of the cell themselves. No.
is it like in the ballpark of where your the kind of substrate stiffness would be?
I guess so, but I don't know.
Much smaller?
No, but he's asking for the stiffness, right?
Yeah.
Yeah. So, and this is also the range of substrate stiffnesses that we explored. So that's why I'm guessing it's similar, but we didn't really measure it. Okay, so then the idea is to start from something I did during my PhD, where we studied this two-dimensional wetting transition of monolayers of cells that either spread or retract. And this defines a wetting transition. And the way we thought about it was it's active because it emerges from the competition of two active forces, which are traction forces that tend to make the tissue spread, and contractility, which is cell-cell active pulling forces that tend to make the tissue retract. And the competition between these two defines a regime of spreading and a regime of retraction. And so the basic idea is if we only focus on the basal cell monolayer of all of this aggregate and forget about the rest, then we just want to write down a force balance for this layer. And if we do that, this force balance will be some internal forces emerging from the divergence of a stress tensor, balancing the forces that are exchanged between the cell and the substrate. And so these forces come in two types. There's friction proportional to the velocity at which cells move on top of the substrate. And then if cells are polarized, they'll also exert an active traction force to walk on the substrate. And in practice, the cells that polarize are the ones at the edge of the monolayer, and these are the ones driving the spread through this active traction force. Okay. Now, I also need to tell you what the stress tensor is. And so here, we also have two ingredients in the stress tensor. One are viscous stresses that emerge from cell-cell friction, and the other one is this active contractile stresses of polarized cells that pull on one another. Okay, and so these are precisely the two active forces that compete against each other and define this two-dimensional wetting field. And so now what we did was to say, okay, if we want to explain Durotaxis with this model, we should make some of these forces depend on the stiffness of the substrate. And so yes, exactly. So so this is an anisotropic active stress that is then also localized at the edge where the polarity is. We also tried with a uniform isotropic contractility, but it doesn't. So the key message of this paper was that this wetting transition, which is active because it's this competition of active forces, unlike classical wetting, depends on size. So if you go to large sizes, then the tissue always wets. If you go to smaller sizes, it never wets. And this is unlike classical wetting. If we do it with the isotropic contractility, we don't capture this effect. And this was in the data.
What the index on your
Oh yeah, this is for interface because it's it's an active stress like this one, but it's at the interface between the cells and the substrate. Yeah.
you take into account the displacement on the substrate or the actual elasticity of the substrate?
No, and this is a point that would be now very interesting to do because for many reasons, but in particular, what I'll say at the end, I think could benefit from now doing elastic capillarity and really looking at how the forces inform the substrate, etc. It's something that we ignore here, and I don't really know what it would do. Yeah. Okay, so then based on this model for two-dimensional active wetting, what we wanted to do was to say, let's generalize it to include stiffness dependencies. And so the forces that could, in principle, depend on stiffness are friction and active traction, the cell-substrate interaction parameter. Okay. So what we did was to make stiffness, you mean just, just isotropic analysis. Yes, that's both ones. No, the Young's model without the, yeah.
But it could be anything.
It could be,
It could be any gradient substrate, any parameters.
yeah.
Depending on the parameter.
Yes, but for, to compare to experiments, what they measure in experiments is essentially the Young model. And so to us, that's the readout of substrate elements.
But could it be something that, I mean, the stiffer substrate has a higher density of collagen or whatever polymer you're using, right? So in principle, it could be something like, it's hard to disentangle this.
Yeah, but yes, but there are also different ways of doing substrates of different thicknesses. And in particular for Durotaxis, what they did here was not to vary the concentration of polymer, but just polymerize more or less. And so it's also a different way. Yeah, different degrees of problem. Okay, so then the idea is to say these two parameters will depend on stiffness. Which functional form should we take? We based it on data, and the simplest functional form that was reproducing measurements of traction forces as a function of stiffness was this one here, which simply corresponds to a linear increase of the forces at low stiffnesses, and then eventually a saturation at high stiffnesses. And the saturation has to take place because cells cannot exert infinitely high forces if you go to very stiff substrate. Okay, so this is the simplest possible functional form that does the job, and it fits experimental data, as I said. So this was what we did in this paper, and with this you can explain Durotaxis and even coherent Durotaxis. So this does part of the job, but it doesn't capture this non-monotonic dependence they showed in this last piece of data that I showed. Okay. So to do this, then the way we thought about explaining this was to actually finally consider the three-dimensional shape of the cluster. And so the way we do it is we say, okay, now what we had before is just a model for the basal cell monolayer, and the way we're going to model the rest of the three-dimensional cluster is just by adding some surface tension at a certain contact angle, and then the corresponding Laplace pressure. Okay, and so to do this, what we then do is to write down the generalized Young-Dupré equation of wetting to balance the forces, the stresses in this basal cell monolayer with the out-of-plane contribution of surface tension with the contact angle, which we can then predict. And so if we do that, then the question is, can we then recapitulate this? And of course, then the answer is yes. Okay, the model shows this non-monotonic dependence of the Durotaxis velocity on the stiffness of the substrate, and it also captures this dependence on size that Silke, you were asking for. And so now the nice thing about predicting this is that we can also understand it. So let me try to explain where this non-monotonicity comes about. So let's start with why the velocity increases at low stiffnesses. So here, the way we think about it is that as you move to higher stiffnesses, the clusters wet the substrate more and more. And by wetting the substrate more and more, they spread more on the substrate. And so they span a larger range of stiffnesses than before. And this means that now the difference in traction force on one side and the other is bigger. And this difference in traction force is the driving force of the Durotaxis. And so if you have a larger driving force, you'll move faster. Okay? So this is the explanation for this part of the behavior. The tissue spreads more, higher traction difference, faster Durotaxis. Okay? Now the question is then, why does it then decrease at even higher stiffness? And we think there are two reasons for that. So to understand this part, what we need to think about is this behavior of both friction and traction with stiffness. They both increase and then separate. And so there are two reasons that make this velocity go down. One is that friction increases, and just that will slow down motion. That's one of the ingredients. And then the other ingredient, which is very important, is that the traction also increases, but then eventually saturate. So at very high stiffnesses, the tissue is very well spread, and so it spans a large range of stiffnesses, but the tractions are almost the same on both sides because they are saturated anyway. And so now this difference in traction, which is the driving force, goes down, and therefore the velocity goes down. Okay? So it's a combined effect of this saturation of traction and increase in friction that slows the Durotaxis down at high stiffnesses. Okay, so that's the explanation we have so far. And then the last thing that I want to show you is the second surprise of the experimental data. So can we measure this? Yes, this was done before. People did it many years ago. For example, in the group of Pascal, was it your group? No, maybe Benoit. Yeah, in Benoit's group, in the group of Benoit Ladoux, they measured it, and that's actually where we took the inspiration to fit this this curve that I told you. And there are even models that predict this kind of linear increase in then saturation behavior. So this was very well covered already. We just took it as an ingredient.
But for the friction saturates as well.
As well, yes.
So you really need a sort of to tune them. They don't saturate them. They don't saturate at the same place. But
We do take the same saturation, so we do take exactly the same dependence.
your E star is the same.
It's the same for both friction and fraction. Because
Does
in
it
the end,
matter?
yeah.
Does it matter if you have you could make the friction saturate before or after, and that you change this.
Yeah, I think it would matter in, it
Yeah.
would shape the curve that they showed.
Exactly. So you get explore that.
No, we didn't. Yeah, so it was enough for us to, for what we wanted to do. So we didn't go that way, but it's true. It could also shape the curve more. It would have this extra.
Because then you get you get reverse maybe of this where if you let the friction saturate earlier, then you might find that as the opposite.
No, but I think both ingredients are contributing to slowing it down. They never speed it up.
And if the separation happens in the regime where you're still spreading, like that, I guess that's.
I see. No, but you would still then just, then the two trends would compete with one another, but you would still have a peak at the lower speed. So it shifts the big, I think, but not more than that. Yeah. And I wanted to say something else. Yeah, that these models that I was mentioning to Silke, they are based on the kinetics of focal adhesions, for example, some of them. And so in that sense, the kinetics of the molecules in the focal adhesions mediate both friction and traction. So it makes sense to take the same parameters for both. So the final surprise of this was that in the experiment they measured the statistics of cluster displacements. Okay, so what's the probability of observing certain displacement of cluster? And what they see is that for small displacements, the probability decays exponentially. And this makes sense because if you check the literature for single cell migration of a persistent random walk, that's precisely what you expect. There's this exponential distribution of cluster displacement. But then if you go at displacements bigger than 25 microns roughly, then you see that the probability distribution builds this heavy tail. And so this corresponds to rare events that correspond to this very long hop, very large displacements that are rare, but still much more likely than we would expect from a random walk, from a persistent random walk. And so if you then, this heavy tail seems to decay somewhat as a power law with certain exponent. We don't understand why or how. And if you look at the events that populate this heavy tail, what you see is that they correspond to sudden detachments. So an example of that is here. You see that this cell hangs on to the substrate for a while and then it detaches suddenly. And then this triggers a massive displacement of the cluster. So if you look at the events that come out here, they're essentially like that. Okay. And so now we're still trying to understand this. We would like to develop some stick-slip model for these detachment events that would ideally predict the emergence of this heavy tail in the displacement distribution. We haven't done that. We don't really understand how to do it. So if you have ideas, very welcome. Okay. All right. So then, and this is where we can come back to discussions on roughness. Whether the roughness in the substrate can actually generate thinning and so on. I don't know. We're trying to think about that, but we don't know exactly what to do yet. So let me just summarize this first part. Essentially what I wanted to tell you is that we have this idea, or this model of three-dimensional active wetting to explain the emergence of coherent tissue Durotaxis. And in particular, it allows us to capture this non-monotonic speed of Durotaxis as the tissues progress in stiffness. And the theory of three-dimensional active wetting is more general, so it could be applied to other contexts as well. And then we have this funny and interesting observation of these long hops that are rare but more frequent than they should, and they correspond to this sudden detachment. So we're trying to now think about that, and I welcome ideas if you have it. Okay, so this was the first part. So maybe it's a good time to have any remaining questions.
If you say correctly, that you can switch the in-plane forces, but not sort of the vertical forces of the southern third, and that's the southern third.
The vertical as well. So these are the surface tension at the edges of the hull.
But only at the end, is there any?
Or in the center, then you get so because of the surface tension, you build a lot less pressure, and then this pushing on the data center. Yeah, but other than that, so that's really the only out of plane forces that we consider. Everything else is in plane. But precisely the interplay between in-plane and out-of-plane forces is what gives rise to this change in shape that then explains the non-independent.
What about variations of this tension?
Variation of surface tension? Yeah, great. So this is actually, in some previous version of the slide, I had remaining points. This is one of them, and the other one is Fritjof pointed it out. So very good. You pick up all the remaining direction. I think it would be super interesting because in principle, this is another force that is mechanosensitive in a sense. It could depend on the stiffness of the substrate. And if you now make surface tension stiffness dependent, then you could think of Marangoni flow. And this could also contribute to the Durotaxis or oppose it. So it's another fun game to play that we haven't explored yet. Yeah. Sorry. So we assume that the clusters are which key? The P pressure or P polarity? Polarity, yeah. So polarity, we write down an effective free energy that says that we tend to we favor energetically the isotropic state, and then we prevent gradients with pneumatic elasticity for this polarity field. And then we minimize this free energy. So with the following boundary conditions, we say the polarity is maximal at the edge. And then just with that and the equation that we get from energy minimization, you get profiles of polarity. Exactly, yeah. We get profiles, maybe I can draw them. We get polarity profiles that are consistent with the traction forces formation. Okay. So this is the polarity field, and this is the radial component, the radial coordinate, and you get polarity profiles that look like that. And there's one parameter which is the decay length, and this is the boundary condition that we invoke. The polarity is maximal at the edge, and we can fit this directly to traction forces of static monolayers, and they fit. So that's what we do. Yeah. No, the surface tension is just a parameter that we impose locally at the edge. That's it. Yes, exactly. It's like an aster, except there's no defect because the magnitude decays. Yeah, and yeah. So depending on the when we study this wetting transition, then we do it, for example, radially. But when we study Durotaxis, we can do as Tani was saying, and just then take a cross section and solve the problem in this one dimension plus the third one.
Yeah. I was just wondering, so how well is it known how this Durotaxis actually works? Like, how do the cells sense the stiffness of the substrate? Do they measure a stress-strain relationship and respond to that? Like, how do they know what the stiffness of the substrate?
Yeah, it's a good question. There's a full body of work about how mechanosensing and mechanotransduction work in this case. It's very complicated. So maybe, what can I say? So essentially, they target the substrate, so they apply forces on it, and then there's a, the focal adhesions are made by integrins, and then the integrins have adapter proteins that connect them to the cytoskeleton, and these have some very complex dynamics in the sense that if you talk a rigid substrate, then you can stretch integrins a lot, and then this can unfold some part of the protein that will then bind others, and this triggers a cascade. So this is part of the story, but it's much more than that. This is just a simple bit to say that.
So
There are many
proposed
mechanisms.
measures. They apply a given
Yeah.
stress and they somehow, based on this cryptic binding sites, then you can figure out whether there's more of this.
Yeah, in a way, yes. But this is but there are more complex mechanisms that are global instead of saying you locally measure at one focal adhesion complex. Other mechanisms were proposed to be global across the cell, and then maybe it's not as easy to see. But in the simplest of pictures, then yes.
When you have said, what happens to people when it comes to superstate like glass, for example?
Fine. What's the
Because
this is a PAA, so polyacrylamide. Yeah. Yeah, but they still adhere. Also, cells can secrete ECM, so they will still adhere to glass if it's properly coated, and and then they'll still exert attraction forces. They will be on the saturation limit, let's say, of the curve that I show. They still manage. I don't know exactly what happens at the molecular level there, but they still manage to adhere. Okay.
Yeah, it looks like the largest in the beginning without the substrates gradient with 200 kilopascal. Does your Durotaxis data include that point? You don't go up that high, right?
The 200?
Yeah, in the door.
No, I think the gradients. Let me see, but almost. I forgot how which range of statistical the gradients span. I can double check later.
Like the 10. So
Yeah, it's mostly tens, but at least 100. I think they go up to 100. Maybe not 2. Okay, yes, let's go on then. So then I wanted to talk about frictiotaxis. And so the idea here is again to think about Durotaxis, but now for cells that do not adhere to the substrate. Okay. And so what I'll show you is that cells that migrate with an adhesion-independent mechanism can still perform Durotaxis. And that what we think is that what they actually do is frictiotaxis instead, so that they are guided by friction rather than stiffness. Okay. So, and this is this, preprint that I put up down here. So this is again a collaboration between theory and experiments. And so this time the experiments were done by Adam Scheller in the lab of Roberto Mayor at UCL here in London. And the theory we did together with Peter Hampshire, who's a PhD student in my group. And so the idea here is still the same. So this is the same picture as before. You have cells that adhere to a substrate, and they adhere through this molecular complexes known as focal adhesions. And they also adhere to other cells if we're in a multicellular context, and they generate internal stresses, and then they transfer them both to other cells and to the substrate, and through focal adhesions. And then through this transmission of forces, they generate traction, which allows them to migrate forward. Okay, so this is the same picture as before. And I want to stress the role of focal adhesions in Durotaxis in particular, because they do two very important things. One are the mechanosensors that allow cells to sense the stiffness of the substrate. And then they are also allowing the cells to transmit the internally generated forces to drive motion. Okay, so they have these two very important roles that you would think makes them indispensable for Durotaxis. And what I will show is that this is not the case. This is precisely what we wanted to challenge here. And so in the presence of focal adhesions, then it makes sense to build the models that we did before that say cells can sense the stiffness, they can adapt the traction force that they generate to the stiffness that they sense, and then you have this imbalance in traction forces that drives Durotaxis. This is the picture I told you so far. Okay. But now it won't make sense anymore if we study cells that do not form focal adhesions. And so here I'm showing you experiments performed by Adam Scheller in channels. And so he puts cells in channel, And first, he coats the channel with fibronectin, which is a protein of the extracellular matrix. And so in this case, what you see here in color is markings of focal adhesions. And so these cells attach to fibronectin, they form focal adhesions, everything's normal, okay? And I want to point out that the blue signal down here is the nucleus. Okay? But now the other thing that he can do is to coat the channels instead with PEG, polyethylene glycol. And if he does that, then these cells do not form focal adhesions with PEG. This is a substrate that does not provide adhesiveness. Okay? And what you see here is precisely this very important message of this figure is that it's precisely black. Okay? So there's no focal adhesion, and just to show you that the cell is still there, the nucleus is still there, but no markings for focal adhesion. Okay? So in this context, without adhesion, the cells still perform motility, still move. They do something known as amoeboid migration, which is known to be, now this died. Here it is. So this amoeboid migration is known to be faster than adhesive migration, and is known to be basically based on bleps instead of lamellipodia, so the type of protrusion changes. And these are all things that we see as well in these experiments. So this looks like classical amoeboid migration. And so before I show you things on Durotaxis, what I want to do is to describe the physics of amoeboid migration that has been worked out in the last few years. And so the idea, and Guillaume Salvay also talked about it in his talk last week. And so the idea is, let's consider a cell that's confined in a channel, and it's initially unpolarized in the sense that it has a uniform cortex, okay, all around the cell periphery. And now this is a contractile structure, and so it can undergo an instability whereby the cortex pulls itself towards one side of the cell, and then there's higher contractility on that side. And so this keeps pulling material from the rest of the cell. It sets up this cortical flow that's flowing backwards. And this backwards cortical flow then through friction with the substrate generates a force that propels the cell forward. Okay. And so in this case, the cell will move towards the right. And you can understand that, the cell is moving toward the right in this case because symmetry was broken in this particular way. But the symmetry can as well break in the other way. And that's totally fine. And so these are two bistable states, and this is a classical scenario of spontaneous symmetry breaking. Okay. Now, what I want to do is to describe a model that implements these ideas. And so this was developed by Andrew Calanchon and Raphael Baturier 10 years ago. And so the model goes like this. We're going to try to describe the cortex through a concentration of this cortex of actomyosin, which will move together with the cell that propels itself at a certain velocity, capital V. And then we will also take into account the flow of the cortex in the frame of reference of the cell, small v. And then the cortex will polymerize at a constant and uniform speed, and it will depolymerize at a rate that depends on its own concentration. Okay. And so if we encode all of this in an equation for the mass of this, for the concentration of the cortex, we have something like this. And so we have many terms. So if the concentration of the cortex changes, it's either because the entire cell is traveling at a certain speed, capital V, or because the cortex is moving in the frame of reference of the cell. So this is a vective term with a small v. And then on the other side of the equation, we have polymerization and depolymerization processes. And so these just combine to try to set up an equilibrium concentration for the cell cortex. Okay. So this is the equation for the concentration of the cortex phi, but it still has two additional unknowns, these two velocities, capital V and small v. We still don't know what they are. So we need additional equations to specify these two quantities. And so let's start with a force balance for the actomyosin gel. And so this force balance balances friction between the actomyosin cortex and the walls. And it's proportional to the velocity small v. And then it balances this friction with internal stresses in the gel. And so they come again from a stress tensor, which has many contributions. Essentially, they are viscosity of the actomyosin gel, then active contractile isotropic stresses due to myosin contractility. And then in the end, this actomyosin network is a polymer solution. So it has osmotic pressure. You can get this, for example, if you consider, if you model this polymer solution with chlorine-Huggins, this will give you some osmotic pressure, and that's what these terms account for. Okay. And So this will then specify small v. Now, if we want to also specify capital V, the velocity of cell motion, then we need a global force balance, not just for the cortex, but for the entire cell. And again, this is a competition or a balance between two frictions. The first friction is a drag. So if I take this cell and I drag it along the substrate, then there will be dissipation because fluid has to get around the cell through the interstices between the membrane and the walls, or through the cell, through macropinocytosis. The cell can eat up fluid at the front and then spill it out at the back. So either of these processes will generate dissipation, and this is what this drag coefficient is encompassing. And then there's another friction force, which is the cortex wall friction. When you integrate it over the entire cell, this actually provides a thrust force for the cell to move. Okay, so this is the driving force, and then the drag opposes it. So that's to say that this is the model we will be considering. It, when you consider it in uniform environment, it predicts this contractile instability that explains amoeboid migration. And what we will now do is to consider it in the presence of gradient and see if it explains what we're now interested in. Okay.
You top and the bottom, that the thrust of the drag. You have to integrate, but you have to.
Well, the model is 1D, so it doesn't, it really collapses it into just a line. Yes. And it's a 1D model that you don't know where it's.
So how much to think about because presumably it is sort of time travel essentially.
Yeah.
So I should make it.
No, both ways. So the essentially what you're doing is polymerizing everywhere, but including here, and then you flow backwards on both sides, and it accumulates here, and then it depolymerizes here. And so the flux that goes from here to here is of monomers of actin, let's say. So you basically say the top and bottom are identical, so we can collapse them. Yeah. Okay, so this is the model that we'll play with. Okay. And so now we can go back to the experiments and see if cells that behave in this way would perform Durotaxis or not, despite that they lack focal adhesions to sense stiffness. And so what Adam did was to generate channels with uniform stiffness. And then what cells do is they go back and forth. You can see here, and you can see this thymograph, there is this transition between back and forth motion. And this is consistent with this picture that in a uniform environment, you have this 2 bistable state and noise can flip you over from one to the other. But then if you generate channels with a stiffness gradient, then cells instead move very persistently through the channel and they almost never reverse. Okay. And so they perform Durotaxis. And this is striking because they lack the machinery to sense the stiffness. And so when we were thinking about that, we said, okay, if we cannot rely on them sensing stiffness, maybe since this mode of migration is anyway based on friction, it is all due to friction. Okay. And so what we proposed is this idea that this could be actually frictiotaxis. And so the way it would work now that we know about the model is the following. We start from the same unpolarized state as before, but now we put it on a substrate friction gradient. And what will happen? The first, the parts of the cell that are not experiencing friction or much, little friction are the poles. And so these parts will be the first ones to contract. And so they'll start contracting. And once they start contracting, they'll start pulling in material from the rest of the cell. And they will pull it faster on this side because there's lower friction than on that side because there's higher friction. And so because of these asymmetric velocities, what will end up happening is that all the cortical material will end up accumulating on the low friction side of the cell. And this will then power migration toward higher frictions. Okay. And so what you end up with is frictiotaxis in this situation, where the presence of a friction gradient has broken symmetry now externally instead of spontaneously.
Have a membrane between the channel and the cytoskeleton, right?
Yes.
So this friction will go to the sample transmitted to the membrane, right? All the sugar that are sitting on the surface of the cell.
Exactly, yes. So we think about it as non-specific interactions between polymer brushes, essentially. And yeah, but no specific addition. Yeah. And actually we see that because if we don't confine these cells, then they actually can float off. So they are not adherent at all, but yeah. So there's no adhesion, but just friction. Okay,
And what you're varying is the stiffness.
yeah, exactly. So in the initial experiment, what we vary is stiffness. Okay, so how do they even know about it? And so the hypothesis is, okay, they don't know about it, but they know about is friction.
Yes.
But then friction and this mean friction and stiffness have to be.
Yes, but I know. But it's not, I mean, usually you would say that the reason why you know is because you've got some binding, unbinding, some molecules. And then of course, because of that difference in the original binding, then you can sense that friction.
But this is the answer I gave before, but this does not apply now. So now this is an open question whether friction and stiffness go hand in hand, because this model no longer applies. It's instead some complex, non-specific interaction between polymer fractures, and I don't really know what this will be. Okay, so I don't really know in this case a priori whether friction should increase with stiffness. And that's then what they tested in the experiment. So this is the next experiment. Adam, what he did was to take an AFM cantilever and slide the tip on the surface. And when you slide it, then you can measure a friction coefficient from the torsion of the cantilever tip. Okay. And if he does that, then he gets friction coefficients, and they do increase with stiffness. And so this idea that, what the cells are caring about is friction makes sense, even if we provide them with a stiffness gradient, because these two quantities are correlated. And then the final thing that we wanted to do is to actually say, okay, but let's not play with stiffness. Let's play directly with friction. Let's try to demonstrate friction directly. And so this is actually doable in the experiment as well. What you can do is coat the channels in either of two substances. So this is the one we used initially, PEG, but you can also coat it in BSA, bovine serum aluminum. And this is also non-adherent, but it provides a different friction coefficient. And then we can mix both and generate friction gradients. And so that's what Adam did. And so first, if you mix PEG and BSA uniformly, then you get a channel with a uniform coating, which has a uniform friction. And then cells move in the same way as before. They reverse every once in a while. You see this reversal event, which are consistent with pipe stability. But instead, if you flow each of the components from either end of the channel, then you let them diffuse and they generate a gradient in concentration, which corresponds to a friction gradient. And in this case, the cells again are very persistent. They move fast and almost without reversing in this channel. And so this is direct evidence of frictiotaxis. And here I'm also showing, just a representative example. We have statistics of that as well, etc. So this is, then proof that the idea was possible. And so I just want to conclude by saying that what I showed you is that cells can perform Durotaxis even without addition, even without this focal addition that was supposed to be crucial. We think that what they actually do is frictiotaxis, so that they move toward higher frictions. And I think this could be important because there are many types of cells in the body that move through amoeboid migration without really involving addition. This happens in certain types of cancer cells and in the context of the immune system as well. Many types of immune cells do that. And the viewpoint so far was that these cells, for guidance, mainly relied on the chemical system, that they mainly perform chemotaxis. And what we're showing now is that they could, in principle, also be guided by mechanical systems. There could be mechanical form of guidance applying in this context. So what I really now look forward is seeing, experiments from biologists in vivo to see if anything like that happens in amoeboid migration can also, be guided by Durotaxis or frictiotaxis in some in vivo context. And so with that, I finish, and thanks for all the questions and looking forward to more.
But in your first part on Durotaxis, friction value.
So it's a good question. I don't think so. Because you can then also inhibit contractility, and the thing will just not do much. So I think it still requires active force generation. But I think it's an interesting question, and we're trying to do that at least in the theory, regardless of what the cells actually do. we now want to ask the question: can friction tax also take place in a digital environment? And this I don't know, and we're working on it.
But isn't inhibiting contractility make distinguishes? Because if you inhibit contractility in this earlier approach, you also use
Yeah.
right? Because it's also based on contractility in a different way. Right?
Yeah.
I guess it's the heat that you do that.
But this is what makes it hard experimentally, because because the moment, so here it was nice because we could have this friction gradient without the vision and with uniform stiffness. But if you have to provide molecules for the cells to adhere, then it's much harder to engineer friction gradient, because then it can be confused with haptotaxis, which is essentially chemotaxis to bound ligand. So this is much harder, but at least in the theory, we should be able to have symmetric active tractions that would not bias motion, but just would provide activity to drive it, and then have a friction gradient and see what happens there.
Related comment and question. So the nucleus looks like it's about the same size of the channel.
Yeah.
Right. And there are these papers that talk about sort of ability of cells to migrate using the nucleus as a piston, and then taking advantage of the harmonic pressure difference. And that's also independent of any adhesion. You can actually turn off the contractility and it still does it. Right. It's like a plug. So how do you distinguish?
Good question. Yeah, I don't know. I think there could be ways experimentally, because they can also block parts of these pathways and so on. Yeah, but it could be all mixed up there. I don't know. One way where it might address this is now Adam is getting profiles of optimizing concentration, and we'll try to fit those with the prediction of the model that I presented. So if they fit, maybe it says that it's not too bad. It's not completely off, but and if it doesn't, maybe it's going to tell us it's because it's driven by other nucleus. So this might give us some hints, but I don't really know. Good question. You had a question too? Yeah.
So friction taxes only happens, only the symmetry rate required one way or another without the gradient. Without the gradient of friction, you show that it could break the symmetry one way or another.
Yeah, exactly. So this is amoeboid migration in a uniform environment. Yeah.
Yeah. So you see also in without the channel. They are no restriction.
No, actually, without the channel, we don't see that.
Yeah.
And so we have a few hypotheses. This is a very well-known thing. Amoeboid migration. There are several hypotheses. One is that often they actually float up, so then it's hard. But the other one is that you actually by squeezing them, you also recruit myosin into the cortex, and this increases the contractility beyond the level to trigger the instability. So that's the other.
For the active, when you do have a they do break symmetry down. So this is the
Yes. Yeah. Agree. Into the I would guess so. Yeah, it would have to be generalized. I guess yes, but I haven't looked at it. Yeah, in principle, I guess it could have a flow field into the and also a concentration field into the. I guess it should work, but these things, when you do it, then you realize, oh no, something bad happens. I don't know, but I would guess yes. Not that I know, it could be there.
There's this claim, or I get it's the front of polymerization of actins and pushing the laminar flow forwards, and sort of also regarding sort of this not in the channel, but or pretty on the substrate. But this doesn't come into in this model, right? This is only modeling sort of the retrograde flow without actually explicitly modeling this.
Yes.
What's going on in the front.
Yes, but these cells actually perform leveling. So the type of protrusion is not lamellifolium, it's LEPs. So from every once in a while, they detach the membrane from the cortex, and then it expands like crazy, and then they rebuild the cortex again, and then keep contracting the back. So it's a different problem. Yeah, yeah, exactly. Yeah. In the previous one, well, the surface tension in the previous picture was a multicellular property. Was not a property of. Yeah.
I mean, this is more new.
Yeah. So in yeah, in the second model, indeed, motion is driven by a gradient in active surface tension. So there's this, maybe I can show. Here in the model, the internal stresses, maybe I'll show you immediately. The internal stresses in the gel, in the cortex, contain this active contractility, which is isotropic, and this is essentially like the surface tension of the cortex. And this depends on the concentration, so it's bigger on the back than in front. This drives motion. And then the fact of having such a weak cortex in front also promotes levity.
So this follow that. So the flow field that you would have would be some sort of stagnation points, the front and back, and some,
Yeah,
and then some exactly symmetric flow above and below.
exactly.
That's yes, the points. So we have two stagnation points. One is a source, one is a sink, and have to
Correct. Yeah, correct. And then you still conserve mass through the flux that you generate by diffusion of the depolymerized. Yeah, exactly.
So the idea is that because it's proportional to the density and it's more to be there and not wrong, then you have the stability that you need to have the symmetry, right?
Yes.
Okay, why it doesn't happen?
No, I think it should happen in 2D as well. Yeah, I guess the instability should.
There was also have
Yeah, exactly. Yes. Yeah, it should be fun to do it. I haven't done it, but in principle, it should work. Yeah. Yeah, something like that, or yes. So you can either go towards a discrete model with specific adhesion point and thinning sites and so on, or you can also introduce some form of random potential, continuum random adhesion potential, let's say, and also you could make it dynamic in principle, but I would argue for the simplest first. Yeah. Yeah. I don't really know. What I suspect is that either roughness or just inhomogeneities in the coating could provide heating points, and then some cells attach. This would be the simplest picture. A more complex one would be that the cells themselves, their dynamics, generate stronger every once in a while, and these are the ones that remain for so long. But it's hard to disentangle all these possibilities. Yep. Thanks.